Hi, happy Veterans Day and welcome back. Today we're going to be starting on one of the larger modules, which is searching and sorting. It's a fundamental to algorithms, to a lot of other algorithms. So we're going to be taking the next probably 2 weeks, might even take up until the Thanksgiving break to cover everything that we're going to be covering. Because this is the first time that we're going to actually be looking at algorithms and a little bit, an introduction to a little bit to algorithm analysis and determining here's one method of doing something, here's another method of doing something. They both accomplish the same thing, but can you say that this method over here is better than this method over here as far as efficiency goes, okay? And we look at these things through the lens of searching and sorting because those two operations are fundamental to any data crunching operation. Lots of different algorithms expect you to have the input sorted in a particular way so that it can do things that operate on it, or as a pre-processing step to an algorithm, it'll sort it and then it'll go on and do things. A lot of times you have greedy algorithms that want to choose the best local choice so far. So in other words, that means maintaining an ordering of some sort, choose the cheapest thing there, right? So finding the cheapest things, searching through, finding things, keeping and maintaining order on things, those are two fundamental operations. There's also a large variety of algorithms that have been developed for these things. There's no less than a dozen sorting algorithms, and every CS course has some visualization tool. I think if you go to sortingalgorithms.com or something like that, you can visualize a dozen or so different sorting algorithms. It's nice and pretty, but what I'm going to do is I'm going to look at these algorithms through the lens of efficiency and practicality. In other words, we're going to look at the algorithms, and we might even develop some of them and code some of them up, but at the end of the day, you don't roll your own. You use a library to do this stuff for you. And for that, I'm going to show you how to use the C's library. Every language worth anything is going to have some sort of way to search and sort through elements. You just need to be able to plug in that last little key in order to enable it to determine how to order things. In other words, given these two things, do they go like this? They're in order, or they're out of order, so I need to swap them, or they're equal. So I found what I'm looking for, right? And so those are that's going to be from the practical perspective. So we'll start with the easier one, ostensibly easier one, searching first. And even for this, you have to ask yourself a lot of questions here. It's not just a matter of looking through and finding what you're looking for. You have to ask yourself, what are you searching? What are you searching? Is it an array? Or another data structure. Right? We haven't looked at any other data structures yet, but you can also ask other questions. Are you searching for strings, integers, doubles, or user-defined types? Right? For example, students, or RSS feeds like you did last week, or what you're doing right now, airports, right? Etc. Are you searching through just numbers, or are you searching through objects or things, structures, right? And another question is, how are you searching, right? In other words, not algorithmic, I don't mean not algorithmically, but by what criteria are you searching? Right? So for example, if you have a collection of airports that you're working on right now, I want to search through and find the closest one to me right now. That would involve doing an air distance computation. If I just want to search through and find all of the airports in Nebraska, I would be searching according to the state. If I want to search all airports in the United States, I'd be searching according to a different criteria. If I'm searching for one particular airport among all of them, what would I be searching for? What uniquely identifies an airport in your hack this week? Or last week, a GPS ID, right? Global Positioning System Identification Number, right? So by what criteria are you searching? Are you searching based on some string value, some integer value, or something more complicated like an air distance calculation? You could search for a particular element, right? The minimum, or maximum. Those are two things that you've already done, right? And you've searched through and found the minimum, the maximum. That's a search criteria, right? Or median, right? Or mode, etc. Right? You can search through all of those things, or in general, the ith order statistic for all of those. There are many basic and advanced criteria that you can search for. Right? You have to be specific when coding, but be general when talking about algorithms. Right? When I talk about an actual algorithm, I'm going to be using something called pseudocode. That's fake code. In other words, those are all excellent details that you do have to think out and come up with the answers to. But at the end of the day, if I'm just developing an algorithm, I don't want to have to worry about those details. I want to develop one master algorithm that specifies how to search and then not have to worry about that algorithm. Then when I go ahead and implement it somewhere, the same basic algorithm will have one implementation based on some criteria, slightly different implementation based on a different criteria, but at the end of the day, it's all the same algorithm. Right? I want to be able to develop generic algorithms in order to solve these problems. Okay? Another question, one question I missed up here, I'll go ahead and put it up here, is how do you determine a successful or unsuccessful search? Right? How do you know that you found what you've been looking for? Right? So we're going to answer all these questions with a simple example that we're going to develop right here called linear search. Right? Okay? And for this example, I'm not going to do pseudocode at first. I'm going to do something familiar. Let's develop this in C. Right? So the objective here, let me go ahead and start my documentation style comments here. This function searches the given array of what, which is of size what, for the given key element. Generally, when you're searching for something, you're talking about needles and haystacks. So haystack, that would be your array, and your needle would be the key. The key that you're searching for. I want to search for this element that matches this criteria, right? The one that's closest to me, or the one, the airport that's closest to me, or the airport that matches this GPS ID, or the all airports that map, the Nebraska as a state, right? So to keep this simple, let's go ahead and make it more specific. Array of integers, okay, of size n for the given key element, all right? I'll come back and we'll augment that later. I'm going to call it linear search, and we'll understand why it's called linear search later on here. Help me out. What inputs do I need to give to this function? I need to give it the array, right? Int star ARR. Now, am I going to be making changes to that array? Nope, so I can make it const to advertise the fact that I'm not going to make changes to those arrays, to that array. And I've already said that the size is n, so I need to do my own bookkeeping. Now, finally, I need a key. So if I'm searching through integers, there we go. If I'm searching through an array of integers, what type is my key going to be? An integer, okay. And what will I call it? I'll call it key, because that's what it is, okay. Now, what's the return type here? That's the other design question that we need to answer here. We need to ask for, how do you determine a successful or unsuccessful search here? Unsuccessful search. There we go. So here's your haystack, which is now an array of integers. Here's your needle, key. I'm searching through the matching haystack. I'm searching through the actual needle in the haystack. What kind of a question do you want to ask? You could ask a question of, does there exist this key in this haystack? In other words, is 10 in this array? What kind of an answer would you expect back? True or false, right? You're asking for a Boolean value. Yes, it contains that key. No, it does not contain that key. Is there another question that you could ask? Maybe even more a general question. I not only want to know whether or not the key is in the haystack or not, I also want to know where it is, right? So how could I tell you, yes, it's in the haystack, and it's at index 5? How could I do that? By returning the index value, right? So I'll go ahead and say that my return value here is int. If you want a Boolean version of this, that's perfectly fine. I would have said contains instead, right? It contains yes or no, and of course it would still be an integer as a return value because that's how C works. There are no built-in Booleans. So this function returns the index value at which of the element that matches the key. So wait a second. I'm searching for 10. What if there are multiple values of 10? Do I want the first one or the last one or all of them? Right? I want an entire list of all the indices that contain the value 10. Right? Well, those are all variations that you have to ask yourself with all these questions up here. Do we return one value indicating the first element? Well, I'll just go ahead and specify that. We'll keep it simple, and we'll say that the first one that matches, that's the one that we'll return. The function returns an index value of the element that first matches the key. Okay, there we go. So let's go ahead and develop this algorithm now. Help me out. Okay, a for loop, an idiomatic for loop here. Why? Because I'm going to search through the array starting at the first element. While I is less than n, I'll be consistent here with my white space. While I is less than n, I plus plus, I'll ask the question, if the array value at the index I is equal to the key value, then I'll return what? I, the index at which I found it. It stops at the first, so if there are two values of 10, in the, here's a value of 10, here's a value of 10 in the array, it starts at the beginning, goes through, finds the, oh, that one matches. I stop and I return that value immediately. I never found this one over here because, well, that's a different function. Right? Find all or find last or something like that. Find last, what would you do? You'd start at the end and search towards the beginning. Okay? There's still an issue here, though. What's the issue? Let me go ahead and cut and paste this into REPL and see if it complains about anything. It does. You can't see it. It's green right there. There we go. So what's it complaining about? Let me go ahead and hover over it. Control may reach end of non-void function. So what's the other case here that I need to think about now? Remember the questions that I was asking before are, how do you determine a successful search? Well, I'll return the index at which I found it. How do you determine an unsuccessful search? Exactly, it's not there, right? Not found. So return what? What value would indicate an unsuccessful search? Think about error handling here for a second. Error handling, you generally, if it returns a pointer, you return null. If it returns an integer as an error code, you return some non-zero error code value here. If I return, say, 1, well, I'd have an ambiguity problem there, right? That'd be saying that I found it at index 1, and that's not the correct way. So is there a value that indicates no index or an invalid index? Some negative number. Right? Give me a negative number, the simplest negative number. -1. Right? I'll return -1. And I will want to document that. That this function returns -1, oops, in the event that no such value is found. Right? You put that in the documentation, explain how to use this, and that's great. Now anybody can read this and understand in plain English that that's how it works. So I can check, is it negative? Well, then that means that I can answer the first question of yes, it's in there, or no, it's not in there. By simply but I'm returning more information here. So you could do basic error checking here as well. If array is null or the size is negative, then you could just return, well, what? How do I do error handling in this case? I want to know does this value 10, can you find it in this non-existent array? What's the answer? No. So what answer was I returning down below for no? -1. I could put that in there in the documentation too. Returns -1 in the event of no such value is found or an error is encountered. Right? That's the magic of documentation. You're giving other people, you're advertising the behavior of your algorithms. You're documenting them. Okay? Now, usually this documentation belongs to the prototypes, but this is just a demonstration, so I don't have any prototypes here. Right? All right, that looks pretty good. Let me go ahead and cut and paste that and see if REPL is now happy with all of my syntax, and it looks okay. All right? Now let's see a demonstration of this thing. Okay? Let me go ahead and say my key value is, I'll search through for 4. Right? And I will say index of is equal to linear search of array n and key. There we go. And then printf, I'll print out found %d at index %d. And the line, I found the key at index of. There we go. All right. And let's run this and give it, let's see. Where would I have found it? I found it at index 3, 0, 1, 2, 3. There's the first instance of 4. It didn't find the second instance of 4 because that's not how I wrote the algorithm. That's not how I wrote the function. Okay. Well, let's search for something else here. What if the key value is instead 2? Where would I find that? At index 8, right? There are 9 elements in there, so it goes from 0 to 8. Okay, that's a successful search. I'll probably also want to see an unsuccessful search. Search around for 10. That should return -1, and it does. All right? Now, of course, my message here is founded at a negative index. I would need to change that and check to see if it's negative, then report that it's not there. Okay? How does this actually operate? So let me go ahead and cut and paste this, and let's see what the code visualizer does with this. And unfortunately, it's probably not going to visualize it very satisfactorily. But let's go ahead and see it in action here. So next. There it is, 10. Go into index. Oh, excellent, good. It does have it has an array pointer. Unfortunately, I is only going to increment I. Okay. You can see that as I increments up here, it checks the first one, then it checks the second one, then it checks the third one, then it checks the fourth one, all the way until it gets to the last one, index 8, breaks out of that for loop, sees that it didn't find it in any of the 9 elements, and so it ends up returning -1. Right? What if instead we searched for 5? Right? And visualize this execution. How many steps are there now? Only 13 steps. Did anybody notice how many steps there were the first time I ran that? How many steps were there? All right, well, we'll go back and see at least. Here, there's only 13 steps. It goes into the function, right? Does its error checking, then goes into a for loop. How many times is line 8 there executed? Oh, there you go. I found it. I found 5 at the very first one, and it ends up returning immediately. Right? So it only had to do 1 comparison, right? Let's go ahead and edit this code back to searching for 2 and visualize this execution. So there are 13 steps to search for something that you got lucky and it was immediately there. There are 29 steps here, right? So nearly more than double, right? Or yeah, just exactly double here. Some of those steps don't have anything to do with this algorithm, but you can see that searching for something that doesn't exist is going to cost you a lot more in terms of computation time, because it's going to have a lot more iterations of this for loop, right? So we can characterize this as a best case scenario and a worst case scenario. Best case scenario, how many comparisons is this function going to end up making? 1, right? Worst case scenario, how many comparisons on line 7 or line 8 is this function going to make in the worst case? The worst case would be when you don't find anything, or you find it in the last place you're looking for, the last element. And how many elements are there in general? Somebody said it over here. N. So in the worst case, you're going to be making n comparisons. Well, you can't be an optimist all the time, but maybe you don't want to be a pessimist all the time. Is there some in between? What about an average case? On average, how many would you expect? And over 2. Where did you get that?
N versus like n plus
Focus.
1 divided by 2.
Oh, okay. So you took the best case plus the worst case, and then you average them, right? So that would be equal to n plus 1 all over 2. Well, we're off by 1, but who cares? We'll just say that it's about n divided by 2, right? And this is the worst case, this is the best case. I just flipped them around. So it's about n divided by 2. So best case scenario, you get lucky and you only have to make one comparison. Worst case, you have to make all n comparisons. The average case, you only have to make n divided by 2 comparisons. Right? Now, that's the naive way of looking at it, and it turns out that that's exactly the correct answer, n divided by 2. If you wanted to do a rigorous analysis of this, you'd have to go through and have define a probability distribution that maximizes the number of comparisons, and then have a probability distribution of an unsuccessful search, and then do a bunch of calculations and come up with a summation, solve it in a closed form. But at the end of the day, guess what you get? N divided by 2. Right? So the naive way of doing this is it gives you the exact same answer. Right? So n divided by 2, or n, gee, what kind of a function is this? If I were to write this out as a function, f of n is equal to n, or say f2 of n is equal to n divided by, or 1/2 n. Characterize those two functions. What kind of functions are those? They're linear functions, right? If I were to plot them, what would it look like? Well, here's n, right? What would n divided by 2 look like? Has a slightly smaller slope, right? So there are your two functions that characterize this algorithm. They're linear functions, both of them. Which one is better? Can we make that value judgment there? Which one of these is a better function? Well, what are we measuring here? So this is n here. This is the size of the input array. What is this measuring on the y-axis right here? Number of comparisons. And number of comparisons has a direct correlation to computation time. Right? So computation time, higher is better or lower is better? Lower. Why would lower computation time be better? Because it means it's faster, right? So now let's make that value judgment. Which one of these is better? Yeah, this one, because it's lower. So fewer number of comparisons on average, better computation time because it's faster, right? Lower is faster. Faster is better, right? Unless you want to slow computation. And by the way, there are several instances in which you want to intentionally slow down computation time. One of those is people trying to break passwords. An adversary trying to break password, you want to slow them down. You want to force them to invest CPU cycles to slow them down. What's another application that you might be familiar with? No? Nobody does Bitcoin? What Bitcoin mining? Anybody do Bitcoin mining? Nobody? Really? All right. Use the university power for all you can, right? Just don't get caught. But you can do Bitcoin mining. Bitcoin mining is intentionally slow because they want to. The design of the system is that they want to limit the growth of the number of Bitcoins that are created. So it's designed such that you are forced to invest computation time to find Bitcoins. That's what Bitcoin mining is all about, right? It's actually the same principle, hashing and slowing down hashing. But in general, you want better, faster computations. Now, both of these are linear. So now we don't require calculus in this course, and I'm not going to require it. But put on your pre-calculus or calculus hat for a second, and tell me about the growth rate of both of these functions. How would I find the growth rate? What characterizes the growth rate of a function? The first derivative. So what's the first derivative of n? 1. What's the first derivative of 1/2 n? 1/2. Right? So from that perspective, this it doesn't just have to be a graphical lower is better. The growth rate of the function. If you can say that the growth rate of this function is lower, that means that its curve will be lower, and therefore it will represent a faster algorithm. Now, this was the same algorithm. It was just a different way of looking at it, a different perspective of looking at it. But if I had two different algorithms, and one of them looked like this, and the other looked like this looks more linear, and maybe another one looks like this, right? Say that this is logarithmic. And this is, say, n squared, which is quadratic, right? Then you can start making value judgments. Now, if you just look at a section of the graph right here, well, which one is the best? The linear, this guy right here, right? But is that the best overall? Remember, you're not interested in small input sizes, right? You're interested in larger and larger input sizes. An array of size 1 million, not an array of size 10, who cares about that? An array of size 1 million, an array of size 1 billion, an array of size 1 trillion, big data over here, right? When you expand out your, now it doesn't cross right here, by the way, it's just a terrible drawing, so we'll cover that up. Now when you expand out your consideration, oh yeah, sorry, it does cross, linear goes past this, but logarithmic stays below it. If you expand out your consideration as n tends towards infinity, now which one is better? The logarithmic. Right? So you can start to make value judgments on the relative efficiency of algorithms if you can start to characterize them in terms of the number of operations that they perform. And this is why we call this algorithm linear search. Why do we call this linear search? Its behavior is linear. Come on, there we go. It fell asleep, sorry, a second. There we go. There. All right, its behavior is linear. That's why we call it linear search. That if you give it an input of size n, it will make roughly n divided by 2 comparisons on average, or n comparisons in the worst case. You can't always be thinking about best case and saying, oh, it only ever makes one comparison, right? Only in a very small minority of instances will it actually do that. But now we'll revisit that all in, eventually as in more formal setting here. But there's still a problem, a practical problem. The above solution is only good for searching what? A number, in other words, and what kind of numbers? Integers. Right? What if I wanted to search for doubles instead? Copy, paste, or copy pasta. Linear search, first of all, can I name it linear search? No, for doubles. Right? Okay, well, how would I change things? This would be a double array now. My key would be a double, but guess what? It doesn't return a double because of double. It's still returning an integer for the index value. Is there any other change? No. Right? Okay, fine. What if I wanted to search through and do an int linear search for strings? Right? It might look a little bit differently, but you still take an array of strings. You still have, instead of equals equals here, you would use strcmp. Right? What if you wanted to do a linear search for airports? Right? Well, by what criteria? By GPS ID? ID. I don't even know how to do that. ID. We'll do that, right? All right. Well, what if I wanted to search by state? Right? What if I wanted to search by blah 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 blah? I'm going to stop it there. Right? Is this a good idea? About how much of this code would be repeated? Well, the same error checking, the same basic for loop. The only thing that would change is this right here. How are you doing your comparisons? Are you comparing your airports by their GPS ID? Are you comparing your airports by their state? Are you comparing your doubles by using equals equals? Are you using strcmp? Only one line changes. Are you going to copy pasta an entire function, pollute the namespace with a different name for each one? Is that a good idea? No. So the above is only good for searching one thing. Our ultimate goal is to write one function that searches for any type of data by any criteria, or criterion, right? Or actually criteria. You could have multiple, right? Plural. Right? So that is going to take a little bit more work, and that won't be the focus of today. Instead, the focus of the rest of the day is to improve this. Can we do better than linear? Right? Binary search. So linear search requires about n divided by 2. I'll go ahead and leave it like that. I could put this into LaTeX mode, but it won't render on GitHub anyway, and I'm not rendering it here. So linear search requires about n divided by 2 comparisons, operations on average. Right? Can you do better? Right? Consider for a moment, what if the array is already sorted? Right? So if it's already sorted, what I'm going to do is I'm going to jump to the middle of the array. Right? And the middle of the array is automatically m. Well, you can say that it stands for m for middle. But what's in the middle of an array if it's sorted? The median, right? So that's also the median element if you want to look at it that way. And then the rest of the elements, A1, note that I'm using mathematical indexing on this figure here, A1 through AN, keeping it general. But if I jump to the middle here, n divided by 2, the element at index n divided by 2, if I call that m, everything to the left, A1 through AN divided by 2 minus 1, is going to be guaranteed to be less than m. Everything greater to the right is going to be guaranteed to be greater than m. Right? So how does this help me in my search criteria? Right? So binary search. Consider if the array is already sorted, what can we do? Consider the middle element m at index n divided by 2, and of course floor, truncate it, whatever. Right? First of all, if the key, the thing that you're searching for, again, we're going to use the same exact terminology again. If the key is equal to m, then what? You got lucky, right? That's exactly what you were searching for. So stop, right? Stop. You found your needle in the haystack, right? And this terminology is actually used in programming languages. Like PHP uses needle in a haystack in their documentation. Right? Otherwise, what if m is greater than the key? Let me go ahead and go with like this. Key is less than m. Right? What if m is greater than the key? Let's go back to the figure over here. So here's m, and the key that I'm searching for is less than it. What can I do? I can look at the left-hand side. Why would I not need to look at the right-hand side here? Because the key that I'm searching for is less, and everything over here is greater than m. Okay, so proceed to search in the left half of the array. Right? That is indices 0 through n divided by 2 minus 1. I don't include n divided by 2 there because I already checked it, and it's not equal to the thing I'm searching for, so I need to look somewhere else. Otherwise, if the key is greater than m, or let me go ahead and write it as m is less than the key, then proceed where? To search in this case, m is less than the thing that we're searching for. So the thing that we're searching for is greater, and I would need to search in this half of the list. Okay? So proceed to search in the right half of the array. Right? Indices n divided by 2 plus 1 through n minus 1. I'm automatically correcting here. I'm going to 0 indexing on this, but 1 indexing on the figure here. Right? So why does that help? How does that help? It effectively removes what? Half of the list. It removes half of the array. Each comparison removes up to approximately about half of the array each time. Right? So maybe we can get away with fewer number of comparisons. For that, I'm going to simply turn to the book, right? And we're going to walk through this. Right? There we go. So we're going to be searching for, let's see, what are we searching for? Search for, I forget what we're searching. Oh, I guess we're searching for 64 or something like that. Well, here. So examine the middle element, which is 12. Okay, yeah, we're searching for 64, something that does not exist, because I wanted to find something that, or I wanted to define something that would lead to an unsuccessful search so that you can see this process all the way back down until you get to one element. So we jump to the middle here, which is index 5, and the value here is 12, which is not equal to the thing that we're searching for. Since 64 is greater than 12, we know that the left half of the list, I've crossed it out here, because we know that 64 is not going to be there. I'm searching for 64 here. So all we need to do is concern ourselves with 6 through 10 and search in that region. So on one hand here, I'm going to keep the number of comparisons. I only had to compare it to 12 to see that that's not the thing I'm looking for. And by the way, all right. Sorry about that. All right, I usually check the charge there. So anyway, all we have to do is proceed with the right side of the list. We then look at the middle element of that right list. Now we're only down to 5 elements here, right? And we look at the one on the at the middle, right? We can jump to that because of indexing. And it's 102, so that's not the thing that we're searching for either. This is my second comparison. But I also know that I can cut out these 2 elements here because those are not the things I'm looking for either. 64 is less than 102. Right? Proceed. Now I only have an array here of 2 elements, 34 and 42. My middle one, because of truncation, will be the first one, 34. That's not the thing that I'm looking for, but now I've got 3 comparisons. And so I continue until I get down to 1, the last comparison, 4th comparison here, and I find that it's not in there. So I output, like I did with linear search, I'll output -1, an unsuccessful search. If I did linear search on this, though, how many comparisons would I have had to make? 11. Why 11? Because there are 11 things in there. I would have started at this end, compared, that's not the thing, that's not 64, that's not 64, that's not 64, not, all the way up to 10. Okay, well, it's not in there. Right? But I can exploit the fact that it is sorted in order to cut it down to 4 instead of 11. Now, what if it's 1,000,000? Right? The savings are even greater, and we'll understand that after we develop this here. Okay? Let's see. So each comparison removes about half the array each time. In general, I'll leave that blank for now. Okay. What does this remind you of? It's kind of a divide and conquer strategy, right? I look at the middle and I'm able to cut out half of it. I look at the middle and I'm able to cut out half of it. So if I start with 8, I cut out half. I cut out half. I cut out half until I get down to 1, at which point I stop. Is this the thing I'm looking for? Yes or no? Well, and I've got my answer because now it's empty. What kind of a technique does that kind of bring to mind? Recursion, right? Exact thing, the thing that we just looked at last week on Wednesday. You can look at this algorithm as a recursive algorithm. That I will look at the thing in the middle, and I will recurse on either the right-hand side or the left-hand side, right? But I'm not going to show you the recursive version, right? There is a clear recursive or divide and conquer strategy to this algorithm. Right? But in general, why do recursion when you can simulate it? Instead of recursion, we're going to look at an iterative version. We'll develop an iterative version of binary search. Okay? Binary, there we go. Well, why is it called binary? Here's the array. I cut it into 2 parts. What is 2? Binary, right? 2 of them. If you cut it into 3 parts, there is an algorithm like that. It's called, what do you think it's called? Ternary search, not trinary search, but ternary search. And quaternary search, I guess you could say. But it turns out that those really aren't all that valuable because at the end of the day, when you draw their graphs, they're all the same graph, right? All asymptotically. And we'll get to what that means later on. But let's develop an iterative strategy here. And for that, I'm going to go ahead and get rid of that visualization. Instead, let's go ahead and come over here to REPL, give myself some more real estate here. And I will go ahead and have the same basic signature. I'll call it binary search. And we will take all of this stuff just as before. Now, if this were recursive, then I would have to pass in a whole bunch of other things. I would have to pass in the indices. What I would do is I would start my index at 0, lower index at 0. I would start my upper index at the end, n minus 1. And then I would make a recursive call. If I recursed on the right-hand side, side of the list, I would update this index. If I recursed on the left-hand side, I would update this index over here. Okay? But I don't want to do the recursive version unless you want to see it. Do we want to see it? All right, I'm not seeing any affirmative head shakes. So let's just go ahead and do the iterative version. Okay? For this, I will still keep my indices here. Int, left, and right. So the idea here is that when I start out, I need to keep track of a left index and a right index that gets updated. The left index will get updated to 6, and then the right index stays the same here. But on the next iteration, when I move down, then my right index gets updated to 7, so that I'm always zeroing in on the element that I'm looking for. I'm always moving these indices one way or another. And the left index and the right index, I need to initialize those. In fact, I'll go and do them on different lines here. Where should I start my left index? 0. Where should I start my right index? N? Careful. -1. Why? Because of 0 indexing. Okay? Okay. So now think about this strategy. Left index, right index, left index, right index. They're moving in on each other. At what point, think about the base case if this were recursive. At what point would I stop? When they're the same, I still want to look at that one element though, right? So when they've gone past each other, right? So I will want to continue this, and I'm using a while loop as most natural here because I don't know how many iterations I'm going to end up doing. I could get lucky, and that's the thing I'm looking for right in the middle, right? I could get unlucky and result in an unsuccessful search, having made these 2 indices pass each other without finding it. So while left is less than or equal to the right index, I will continue checking for it. All right, I'll have an index m. This is going to be my middle index, as per this demonstration over here, right? And that's simply going to be the left plus the right. Oops. How do I get that, by the way? So your averaging technique will work here if it's always the end, right? N divided by 2, right? It's of size n divided by 2. That'll work on the first iteration, but how do I now I've got left and right. Now I'm at some point in the algorithm here, I've got left and right. How do I get the middle element right there, the index of the middle element? Left and right? I could go right minus left. That'll give me the absolute difference, right? And then I could go divided by 2, and that'll give me the length of this thing. So it could be left plus that. That'll do it, right? Or, well, I mean, here's two numbers in a number line. How do you find the middle element with just two numbers? You're taking the what? The average. Right? So left plus right divided by 2. Now, do not do this in practice. In practice, you do need to do what you did. So I'll put a note here. Bad in practice. Susceptible to overflow. Right? In fact, what you want to do is you want to make sure, here's the better solution. The better solution to do exactly what you just said, that right minus left divided by 2, and then you need to add that to your left index plus this. Now, if you take out your algebra hat and you check and you write this out and you simplify it, you'll find out that algebraically this thing on line 11 is exactly the same thing as the one on line 9, but this one is much better code, right? Because it is not susceptible to overflow. You're taking the difference, as long as they're both in range and they're both positive, taking the difference is always going to be positive, and as long as they're, this one is bigger than this one, the difference is always going to be positive, and left plus that and divided by 2, that's always going to be positive and within range, and left plus that value is always going to be in range. This is a much better solution. Right? So I'll go ahead and leave that in there. There's a section in the book that describes use cases for this kind of stuff. That's correct, though, right? 2 left. Yeah, I'm convinced algebraically. Pull out your algebra hats and pens and paper and figure out that it's actually the same thing algebraically. Right? But this one is much better. It's not susceptible to overflow. Okay? In the same way. Now I make my checks. Right? Again, I have 3 cases. If the key is equal to m, that value, or the value at that index, then I need to stop. So if a race of m is equal to the thing I'm looking for, key, then stop and return m, the index at which you found it. Right? Now, m, I'm using that as my index here. A race of m is the actual element that is at that index, and so I'm checking it equality for the key. Else if the array of m is less than the key. What case is that? Where do I need to search for now? The middle element, the key is greater than it. So where do I need to search? Search the right half. How do I end up doing that? I've got left, right, and m. How do I need, which one of these do I need to update? I need to update left and move it to m plus 1. Why not m? That's usually a stock answer as well. Why would I move it to something that I already checked? Right? Just move it one beyond. Right? Again, the visualization over here. If this is not the thing that I'm looking for, why would I keep considering it? I would want to look at this one, m plus 1, through whatever is left in the array. Right? So search the right half, m plus 1. Else if, now there's only one other possibility, but I'm going to write it as an else if. A race of m is greater than the key, or let's rewrite that as key is less than the race of m. I need to search the left half. So if I'm going to search this left half over here, left, right. Which one do I need to update? I need to update right. 2, m minus 1. Okay? And again, you don't need an else if here. You could just get by with an else. But I want to be explicit on as demonstration purposes. Now, if you were to actually write this in practice, then you would do something like this. But if you were actually to write this in practice, I would say don't do that. Use a library, right? And that's what we'll get to by next time, hopefully. Okay. Well, eventually we're going to move left, move right, move left, move right until we get to the, oh, I found it. It's right there, right? A successful search, return m. What if there's an unsuccessful search? And that's what this is complaining about again. You didn't take care of the event that you break out of this while loop, left and right have gone past each other, and so now you need to report an unsuccessful search. Return what? -1. Right? Excellent. Now, let's try this again. Instead of linear search, let's go with binary search. Is this going to work? Let's see. We're searching for 10. Search for 10. Found it at index 9. OK, well, that worked because it was an unsuccessful search. What about 5? That's a successful. That should be a successful search. In fact, there are 2 instances of it. OK. Oh, OK, cool. It found it at index 7. What about 2, which is at the end? Ah, found 2 at index. In other words, it didn't find 2. Is that true? 2 is right there. So what happened? It's not sorted, right? There is a precondition on this algorithm. You can only exploit the sorting if you look at the center and say, OK, I need to go to the left half or I need to go to the right half. If it's all jumbled up and scrambled, you don't have that structure that you can exploit. Right? If you don't have that structure that you can exploit, what do you have to do? You have to fall back to linear search, which is much more costly. Right? So let's see that this actually works. What I'm going to do is I'm going to manually sort this. And by manually sorting this, I mean I'll rewrite 2, 3, 4. Oh, I missed 0 and 1. 2, 3, 4. There were 2 4s, 2 5s. Anything else? 9? Is that all of them? Let's align this to make sure. Yeah, I think I got them all. And now let's try this. Found 2 at index 2. Right? 0, 1, 2. Excellent. What about finding 10? Oh, well, unsuccessful search. So that still works. What about finding, I could get really lucky here, and I could look and find 4 right at the middle index. Right? Because, immediately, I find it at the middle index. Maybe search for 5 instead. Make sure that all of these work. Right? Yeah, I found it at index 7, or 6, sorry. In fact, there are 2 of them. Now, this version of binary search doesn't find the first one. It finds the first one that it finds. Right? So you could have like 56s there. And if it found this random one in the middle, then it would stop and say, I found it, here it is. If you wanted different search criteria, in other words, you wanted to find the first one, well, once you found one, just scan over until you find the first one. Once you find one, and you want to find the last one, scan over until you find the last one. Right? So there are ways that you can still exploit the sorted structure of this. Okay. All right. So is this better? Let me go ahead and cut and paste this entire thing and make sure that it's in the notes. Because if I don't, when I close my computer, apparently REPL likes to refresh and then I lose the work. But it's also in the notes, by the way, and in the book. So there's an implementation, an iterative implementation of binary search. Is it better? Right. So for that, I'm going to appeal to some board work or some paperwork here. Let's see. Let's go back to the .cam. There we go. All right. So my question is similar to linear search. Sorry, there we go. The question is, how many comparisons does binary search make in general. In other words, if I gave you an array, a sorted array, I've already done the work for you. You don't have to sort it. That's our next step. But I've already given you a sorted array of n elements. How many comparisons does it end up having to make? Right? So to do that, I'm simply going to start listing them out. So iteration, comparison, size. I'm going to keep track of all three of these things. On the first iteration, how big is the array? Well, if I start at 0 and I start at n minus 1, how big is the array? N. Right? How many comparisons do I need to do in order to say, well, that middle thing, that's the thing I'm looking for, or I need to search in this half, or I need to search in this half? I just need to make one comparison. And by the way, technically, if you look at that code again, there's an if equals equals, else if less than, else if greater than. Well, so it looks like there are three comparisons, actually. Well, we already saw that you can get rid of the third one automatically because that was just for demonstration purposes. So you do have two comparisons, but really not. Right? In the grand scheme of things, determining whether or not something is negative, positive, or 0, we only count that as one comparison. Because what we're eventually going to do is we're going to be integrating what's called a comparator function. And we're only going to be making one call to that function. Right? And it's going to tell us that the elements are like this. They're in order, they're out of order, or they're equal. Sound familiar, right? What function has that behavior that you've already seen? Something negative, positive, or 0, depending on the relative ordering of things. String comparison, strcmp. Right? So that's the first iteration. Again, technically there's more comparisons, but we're just going to count one. On the second iteration, how big is the how big is it now? How big is the array? We cut it in half, right? So it's n divided by 2. And we only make one comparison there to say, okay, here's half as big, so that's the thing I'm looking for, or I need to go on this half or this half. Third iteration, only one comparison again to cut it into half. Well, n divided by 2 is going to be what? Divided by 2 is n divided by 4. Right? Fourth iteration, one comparison. Now what do we have here? I'm not going to do it like that again. 8. Right? You start to see a pattern emerge here. ... On the ith iteration, we do one comparison. And how big is the array now? N divided by 2 to the I minus 1. Okay. Shift those things so that it looks prettier. Yes, technically I'd have to put a -1 here. I don't want to do that. That's I don't like those things. Right? Mathematicians are always like that. Why is pi 3.14159 blah blah blah? Why does the circle have 2 radians? Right? Because all of the formulas that rely on pi, they all suddenly become a lot cleaner. Right? What if it was like 360 radians instead? We want with degrees instead. All of the formulas that you use, they look much different. And they only made the choice of making it 2 radians because everything, all your trigonometric functions look a lot better when they're simplified like that. Right? So I'm going to take that liberty and say, forget about that -1. Okay. In fact, what you could do here is, well, the iteration, instead of iteration, talk about I, right? And then this is 0, 1, 2, 3, and now it works out perfectly. Huh? So it's just a trick, right? ... Continue. At the what iteration do you have one comparison, and now the list is of size 1, ... So the question is, how many iterations in the worst case does it perform? And that's the question, because look at all these comparisons. 1 plus 1 plus 1 plus 1. All I need to do is figure out how many iterations there are to get down to an array of size 1. And if I have the answer here, then I have a summation of 1 plus 1 plus 1 plus 1 That's my answer for the total number of comparisons. Okay? So the question is, when does this thing get down to 1? In other words, when is n divided by 2 to the I, when is that equal to 1? For what value of I? So solve for I. Again, n divided by 2 to the I is equal to 1. Solve for I. Well, what can I do here? Take this onto the other side. Okay. Now solve for I. How do I get rid of that 2? What kind of log? Base 2. 2 to the I. Right? So if I do that to both sides, right? Base 2, why? Because I want to eliminate this 2 right here. What happens to this I? Comes out in front, log of 2, just like natural log of e, is going to simplify to 1. So this is I. Say what? Negative. Oh, no. Nope, I is out here. There shouldn't be any negatives here. Say what? Not in this case, right? Like log of, you're thinking log identities here, log of negative a or something like that? Okay, all right. So this is definitely our answer. The number of iterations that it performs, the number of iterations is equal to the number of comparisons because of this table that I was drawing, right? Oops. Because of this table that I was drawing, which is equal to, well, that's the number of iterations right there, log, and I'll say it roughly equal to, because we might be off by 1 here, doesn't matter, log base 2 of n. Base 2, we're computer scientists. Mathematicians always use base what? Mathematicians. Humans use base 10. Why? Because we've got 10 fingers and 10 toes. But mathematicians use base e. Right? Why do they use base e? So again, I'm not going to ask you to do it on a test or anything like that, but pull out your calculus hats for a second and tell me what is, oh, no, that's too hard. I don't remember. Yeah, no, actually, no, that shouldn't be too hard. You know what the natural log, the first derivative of the natural log is what? 1 over n, but that's not what I wanted. What I wanted is e to the x. What is the first derivative of e to the x? E to the x, right? So why do mathematicians choose e as their base? Because it's simple. For the same reason that they chose the circle to have 2 radians. Everything looks a lot nicer if you don't have these pluses and minuses all over the place. That's why they chose base e, because that's the value at which the first derivative is equal to itself. You can do the first derivative of any base, 2 to the x. What's the first derivative of 2 to the x? Change of base formula, then apply this trick, and you end up getting like natural log of 2 or something like that, 2 to the x or something, right? Right? That looks right, right? In other words, it's just some constant sitting out front here. Who cares? Well, they don't like constants sitting out front, so they chose it to be e, right? We're computer scientists, though. We're not savages. Computer scientists, they have 10 fingers and 10 toes, but something that is far more important than 10 fingers and 10 toes is zeros and ones, right? So CS always uses base 2, right? If you see something without a qualifying base, like just log of n, this is implicitly base 2. Because as computer scientists, we realize that you can change any log of any base to any other log of any other base. In fact, you did this in one of your very first labs. You had to make a calculator for this. Log base a of n divided by log base A of B. Right? All logs are the same to within a constant. We know this, so we don't care. So we just say, all right, we'll choose the simplest one with respect to binary, and that's going to be log base 2. And it shows up in in a bunch of analysis, for example, binary search. Binary search, you only end up doing log n comparisons, log base 2 of n comparisons. Okay? So, linear search, that performs n, roughly, divided by 2 comparisons. Right? And binary search performs roughly, again, we could be off by 1, and in the best case, we get lucky and don't have to do them all, log base 2 of n comparisons, or comps for short. Now, let's look at that from a couple of perspectives. Let's look at it from the graphical perspective. What does n divided by 2 look like? It's this nice linear function, n divided by 2. What does log base 2 of n look like? So at 0, it's undefined. Where's the first place that it reaches the x-axis? 1, right? 2. At 2, its value is going to be 1, which is up here, right? Which is, right? 2, 2. Okay, so it's going to be right on there, right? And it's going to be like something like this. But there we go. It looks like this. It's very, very slow growing. Don't quote me on this picture. Go ahead and use Wolfram Alpha to graph it if you want. This is log of n. So I will ask you the same question as before. Which one is better? This is n, the array size. And this is number of comparisons. Or you can look at that as time, right? It'll take more time because you're doing more work because you're doing more comparisons. So which one of these is better? Binary search clearly wins. Right? So from a graphical perspective, yeah, that's definitely the winner there. Yeah?
So if you're including, or if you're assuming that what your, can't think of it now, what your array would be, if it's already sorted, wouldn't it be great to also include
So if it's not already sorted, should you to make a fair comparison, don't you also have to include the cost to sort it in order to exploit binary search? And yes, you would in general. But I just want to look at searching in and of itself. Linear search is clearly better than binary search. So if it's free to sort something, then binary search is definitely the way to go. That's what we're going to get out of this. Now, sorting is a one-time operation. So yeah, it's going to be a little bit of expense up front, but expense up front means savings later on. It probably is still the better way to go, right? But we'll look at sorting later on. I want to look at another perspective on this, right? So let's consider a database of 1 trillion records, right? So how big is 1 trillion? 10 to the, 9, is it 9? I thought it was 12, isn't it? Okay, 10 to the 12 records, right? That would be terabytes, so some terabytes of data, right? So typically it's a little, I mean, you can get 4 terabyte hard drives for what, 200? So solid state, 4 terabyte drive would be 300-400, something like that. All right. So we're going to search through your 4 terabyte SSD drive for all these records. Right? Linear search. How many records are you going to? How many comparisons are you going to have to make? 10 to the 12 divided by 2. Well, put that in perspective. Give that thing a name. 500 billion operations. Right? Okay. What about binary search? Here, we only have to take, this is my n right here. This is the size of the database. Log of 10 to the 12, right? What happens, what can I do with that 12? Bring it out front. Log base 2 of 10. That's approximately what? 3 point something, something, something. This is certainly less than or equal to, I don't know, we'll go ahead and make an overestimate here of 50 comparisons. Right? So which one is better? Are you going to want to do 500 billion operations or 50? This one, if you did it on a fast computer, is going to take several minutes. This one is going to take several milliseconds. Right? And finally, we do have like 5 minutes left. Now, the last time I will ask you to put on your calc hat, look at it from the perspective of calculus. N divided by 2, the first derivative of that you already told me. It's 1/2. It's a constant. It's a constant growth rate. Log base 2 of n, there. That should be your bonus calc exam first derivative, because what do you need to do to that? It's not 1 over n. It's 1 over natural log of 2 because of the change of base formula, and then an n. Right? So ignore that. It's approximately 1 over n, just like base e. Is that a constant growth rate? What can you say about that growth rate? Is, as n tends towards infinity here, what value is it, what's going to happen to this number? It's going to go to 0. In other words, the growth rate is slowing. Right? If the growth rate were 0, it would be a constant function. Right? But the growth rate here is declining. Right? The growth, as you get larger and larger and larger, you don't have to worry about the growth rate because the growth rate is actually going down. The function is still monotone and increasing, so you will pay more and more for your comparisons, but the amount that you have to pay more as you go for larger and larger input sizes, it actually goes down because of calculus. All right, we'll continue there next time.